This video explores how to move from microscopic chaos to macroscopic order by building a 2D molecular dynamics simulation using the Lennard-Jones potential. The core question is to simulate n particles in 2 dimensions, interacting via the Lennard-Jones potential. Our tasks include initialization, implementing the Verlet integration, computing forces, and calculating macroscopic properties like the radial distribution function, pressure, and temperature. We are translating microscopic mechanics into macroscopic behavior. We use particle positions, velocities, and pair forces to derive bulk properties like temperature, pressure, and structural distribution. Macroscopic behavior emerges naturally from the chaos governed by Newton's laws. Bridging the micro and macro worlds involves 4 main steps: setup, interactions, time integration, and analytics. We use 100 particles, a 2D environment, and 5,000 time steps. Macroscopic properties emerge from the basic microscopic rules written in about 100 lines of Python. We define the bounds of the simulated system with 100 particles, a density of 0.8, and epsilon and sigma equal to 1.0. The box size L is calculated to ensure the simulated area perfectly matches the chosen particle density. The simulation's universe is set up with 100 particles placed in a box, ensuring the total initial momentum is 0. This code snippet shows the definition of parameters and the initialization of random positions and velocities. To create the initial disordered state, particle positions are randomly placed in the box. Velocities are also assigned randomly, and their mean is subtracted to enforce 0 total momentum, preventing the system from drifting. We simulate an infinite bulk material with only 100 particles using periodic boundary conditions, or PBC. Wrapping positions ensures particles re-enter on the opposite side. The helper function applies PBC to displacement vectors to implement the minimum image convention. The Lennard-Jones potential is the mathematical heart of molecular interaction. It balances strong, short-range repulsion and longer-range attraction. Particles avoid being too close, but still desire neighbors. The Lennard-Jones potential shows the balance between Pauli repulsion and van der Waals attraction. The corresponding code snippet calculates the scalar force based on distance, then uses it to determine the force vector applied to each particle pair. When computing forces, we use a nested loop to calculate pair forces. The minimum image convention is applied to the displacement vector before calculating the distance, ensuring interaction with the nearest ghost image across the boundaries. We use code efficiency techniques like the cutoff radius, ignoring long-range interactions beyond 3 sigma, and pre-calculating powers. Additionally, applying Newton's third law allows us to halve the computational workload. The Verlet integration is the engine of time, involving a 3-step cycle: updating the position, calculating new forces, and updating the velocity. The code demonstrates how positions are updated, periodic boundaries are applied, and velocities are finalized using the forces. The computationally expensive pairwise distance loop performs 3 jobs at once: computing pair forces, totaling the system's potential energy, and computing the virial term, which involves the dot product of force and distance vectors. Bulk temperature is derived from the system's kinetic energy and degrees of freedom. Pressure is explicitly extracted from the particle forces, where the second term corrects the ideal gas state for physical interactions. After an initial relaxation phase, the temperature and pressure stabilize into a fluctuating horizontal band. This proves that the n=100 system has reached thermodynamic equilibrium. We can find hidden structural order in this chaotic fluid using the radial distribution function, g of r. It measures the likelihood of finding a neighbor at distance r compared to an ideal gas. G of r near 0 at small r indicates repulsion. To make gr meaningful, the raw geometric histogram is normalized by the expectation of an ideal gas. This forces the function to trend toward g of r near 1 at long distances. The complete pipeline shows how microscopic mechanical rules, applied iteratively, construct a macroscopic physical reality, moving from parameters to plotted results.